problem 526, beautiful arrangement. So we are having n integers labeled from 1 to n. A permutation of those n integers, which we know about that it is starting from index 1. So it's going to be just, for example, if we have just two numbers, so for example, we have a number 1 and 2, and we also have the index 1 and 2. And we just want to check the different permutations of the numbers of 1 and 2. So we have 1, 2 as a pair, one permutation. Another permutation is going to be 2, 1. And the index is going to be the same, 1 and 2. Yeah, because the index is going to be starting from 1. And we just need to meet one of the conditions. Maybe perm I divisible by I, or I is divisible by perm I. Let's just check. So 1 is divisible by 1, 2 is divisible by 2. It is okay. So we have one possible result. And what about this one? 2 is divisible by 1, and this 2 is divisible by this one. It is also okay, because either one of them is okay, so it is okay. So we have another possible result. So how many different cases? It's going to be 2. Yeah. So this is the problem. And we want to return the number of beautiful arrangements that we can construct. So this is a permutation problem, and because n is 14, if we were to use 14, basically the factorial of 14, factorial of n, it means how many different kind of permutations, but we need to times 14. So according to the permutation, and 14 times n factorial, so this is going to be the time complexity. Yeah, because we have 14 numbers, each one of them going to have a length of 14. And 14 numbers permutations, they're going to be n factorial ways. So what is the result of this number? Definitely it's going to be a very large number. Let's just check that. Yeah, let me just return a 0 and create the factorial. Yeah, the factorial of 14 times 14. Yeah, let's just check this number. Is it more than 10 to the power of 8? Because that depended on whether we can calculate using the brute force. As you can see, it is true. Maybe it is even bigger than 10 to the power of 9. Definitely, it cannot be solved by the brute force. You can see that it is also true. It means we cannot use the brute force to solve the problem. Let's just check what is the result of the value. Yeah, as you can see, it's going to be a really big number. It is more than 10 to the power of 9, so definitely we cannot use the brute force to solve the problem. Yeah. So normally for the permutation problem, for this value of n, it's going to be 8 or 9, that is okay, or maximum 10, that is okay, but it can never be like 14. It's going to be a really big number. Yeah. So another way is we can solve the problem by using a set. If we are solving this problem using the set idea, so the set idea, it means we're going to use the bit dp. So the set idea is that we have a set, and we want to put all those numbers inside of the set. And by using the set, it means from the beginning we have an empty set. Now we want to put the numbers inside of the set and to check how many ways. So our DFS, we're going to use a DFS to solve the problem, but we're going to use the bit dp. So from the beginning, we're going to set a 0. This is our initial state. We want to check from the beginning, from an empty set, how many different ways we have if we have the number of n. So for example, if we have two numbers, but from the beginning there's nothing inside of the set, so we're going to starting from an empty set, and then we're going to try to check one by one. So we have two numbers, 1 and 2. Yeah, we're going to try one first. We want to put one inside of the set, and we're going to check how many different ways. So this is the DFS from an empty set, and then we're going to check DFS from 1, and then we're going to put 2. We just need to permutate. Yeah, we just permutate 1. We want to. This is called let's call this f function DFS, and this is f2. We want to check how many different ways of f1 first, and then f2 first. We're gonna plus them. Yeah. This is gonna be the final result. But as we are using a set, definitely we're gonna use the beta DP to solve the problem, because, for example, inside a set we want to check if three numbers like 1, 2, 3 is inside the set or not. We just need to use a beta DP. We're gonna use the bait. We're gonna use bait 1, 1, 1 as those three numbers 1, 2, 3 inside of the set. If we have a 1, 1, 1, it means this number is 7. If this number equal to 7, it means we have three numbers inside of the set 1, 2, 3. Yeah. So we're gonna define from the left to the right. It's gonna be the smallest number to the biggest number. Yeah. So if this is gonna be 1, 2, 3. So if 1 inside of the set, we're gonna set it as 1. If 2 not inside of the set, we set it as 0. If 3 inside of the set, we're gonna set it as 1. So this is why we can turn the set problem into a bit problem, into a bit DP problem. Yeah. Now the problem comes, how can we calculate this f1 and f2? So for this f1, what is left behind? While we put this 1 inside, definitely we want to check the index. So for the index, it is 1. 1 is divisible by this number, it is okay. So we're gonna execute the f1. Yeah. So for f2, similarly, so currently the index is 1. Yeah. And this number 2 is divisible by 1, it is okay. We're gonna calculate the f2. So for f1, how to calculate this f1? So this f1 means we have a number 1 inside our set, and how many different ways for the remaining set 2, because we only have two numbers. If we put 1 inside, it means what left behind is only 2. If this 2 meets the conditions, because currently if we have this 2, it means the index is gonna become 2, and 2 is divisible by this 2, it means we have one possible result. So this is one result. Yeah. And now we want to check this f2. So what left behind inside the set is gonna be 1, and what is the index? It is 2. So 2 is divisible by 1, so this is also a possible result, and it is only 1. So 1 plus 1 is going to be 2, and this is going to be the final result. Yeah, let's just try to use another case. Maybe we want to try more cases. Maybe we have just 5 numbers. How can we calculate that? So from the beginning, we're going to prepare a state. So this is going to be the final state. From the beginning, the state is going to be we will set it all the positions of the bit as 0, and the final state gonna be 2 to the power of 5 and minus 1. It means, yeah, if all the bit is 1, so this is my final state. So I gonna record one answer. So my answer gonna plus 1. Yeah. So this means for my DFS function, I'm gonna return 1 if I get this final state. Now for 5 numbers, from the beginning, I have an empty set. Now I want to enumerate, so this is my f empty. I'm gonna set it to maybe 0. Yeah. Now I want to check all the possible results. I'm gonna start in the f1, f2 until f5. I want to check all the possible results. And finally, I just need to plus f1 plus f2 plus until to f5. Maybe for f1 I have 100. Maybe 10 possible results, maybe f2, 5, or maybe f5, also 5 possible results. Yeah, maybe the possible result is just 20. So this is the idea to calculate the problem. And we have to use a bit DP because we're going to use our case. So for example, if we just check the first number 1 and 2 first, and so what left behind is 3, 4, 5. We want to calculate how many permutations of 3, 4, 5 also meet the conditions of divisible by I or I divisible by perm I. But what if we have the 2 and 1 inside the set? What left behind is also 3, 4, and 5, but this one has already been calculated. This is why we can use a case to directly get the result. Yeah. Now let's just try to use the beta DP. So we're going to prepare a final state. The final state is going to be equal to 1 left saved n positions and minus 1, because the plus and minus operation is always calculated first. It calculated before this bit saved operation. So this means why that is we have to prepare a parenthesis This means we're gonna calculate the bit saved first, and then we're gonna minus 1. Now I want to prepare a case, and we're gonna use the DFS. From the beginning, I'm gonna prepare a initial state. Finally, I want to call the function. I'm gonna start in from 0. It means nothing inside the set. So if this state equal to the final state, I want to return 1. It means I've already found one possible result. Now I want to check the index first. So the index is gonna be the s dot bit count, and we want to count how many numbers inside the set. So it's gonna be bit count 1. Yeah. So this bit count is just calculating how many ones inside, and basically it means how many numbers inside. If there's nothing inside, so this is 0. But from the beginning, we need to have an index 1. So that is why we have to plus a 1. Now we want to check all the numbers. All the numbers, we just want to permutate all the numbers. It's gonna be 1 to n. So here gonna be 1 to n plus 1. Now we want to check the conditions. We want to check if this number is inside the set or not. So we're gonna use the bit operation. So this is the state, and we want to check this state with the number. It's gonna be 1. Yeah, I always use the left shift, and you can also use the right shift. It always depended on how you're gonna check if this bit is inside the state or not. Yeah. So it's gonna be z minus 1. 1 left shift, z minus 1 positions from the beginning. Z minus 1 is 0. So this one, we want to check if this one is inside the state or not. So if it is equal to 0, it means it is not inside. And we also need to check if I modular j equal to 0 or say modular I equal to 0 if we meet the formulas here. Yeah. If it is not inside and we also meet the formulas, now we want to put it inside. Yeah. So we want to check how many possible results, so I'm gonna define a result gonna be 0 plus equal to the DFS, and with the state, or we just need to copy this one. Yeah, because we want to put this number basically inside the set, and we just want to shift z minus 1 positions of this number, and we want to put it inside the state. Basically, we want to put this number inside the set. For example, this number is 1. And this z minus 1 gonna be 0, and this is just 1. We want to check the first one, this position. Yeah. So it means for the bit, it is the first bit. We just want to check this bit if it is inside or not. If it is not inside, we're gonna set it as 1. And finally, we just need to return the result. So this is going to be the entire code. Now let me run it. Yeah, I did something wrong. Here should be and, because I wanted to check if I meet the condition and either one of them is true, I want to put it inside my result. Yeah, as you can see, it works. Now let me submit it to check. Yeah, as you can see, it works and it's pretty fast. And now let's analyze the time complexity. For the time complexity, first of all, we have this kind of state. So this is going to be this one. It is 2 to the power of 14 minus 1. This is the total state. Actually, we are just starting 0 to this number. It means 2 to the power of 14. There's no minus 1. Yeah. And here, from here, we have a for loop. And this for loop is basically to calculate how many different permutations from 1 to n. Yeah. So this is another 14. Now let's just check, do we have any other more operations? So this is just the bitwise operation. So this is okay. We're gonna use O1, and this one is just the DFS, and this is also the bitwise operation, and basically we use the cast. This is also a 1. Yeah, so the final time complexity is gonna be 14 times 2 to the power of 4, 2 to the power of 14. It means yeah, it should be a smaller number. Similarly, it like 2 to the power of 18. Yeah, normally it's gonna be a small number. That is why it works. Thank you for watching. See you next time.